Chaudhary, and hello everyone. Welcome to this session. I'm Sajid Muharri Chaudhary. I'm the chair of the OSA Bangladesh section and the IEEE Photonics Society Bangladesh chapter. And for today's webinar, it's actually a little late in the semester. It's the dead week in BUET, where I'm a faculty member. Also, a lot of the graduate students there experiencing the undergraduate, postgraduate admission. So they are also very tired. We had Viva yesterday, but I'm sincerely thank everyone who joined us, and hopefully we'll have more participants as the webinar goes on. So welcome to today's session. We are organizing this Enlighten Bangladesh webinar on behalf of the IEEE Photonics Society Bangladesh chapter and the Optical Society Bangladesh section, both of which were formed this year. Today, I'm extremely glad and privileged to welcome Dr. Selim Shahriar as a speaker. We'll be speaking about superluminal and subluminal lasers for fundamental physics, from gravitational wave astronomy to search of dark matter. Before coming to BUET, let me actually introduce the two organizations. So, brief introduction about Dr. Selim Shahriar. I actually had the honor and privilege of meeting him at Northwestern University. I was a graduate student at Purdue University, and as a part of Nanotechnology Student Advisory Council, we went to visit the Northwestern University, where we visited Dr. Selim Shahriar's lab, and he gave us an excellent talk. And that's how I got to know him, and I also wanted to invite him into Bangladesh, and we had the chance to have him here virtually today. So Dr. Selim Shahriar is currently the head of the Laboratory for Atomic and Photonic Technologies at Northwestern University. He's the AT&T Professor in the Department of Electrical and Computer Engineering and Professor in the Department of Physics and Astronomy. He's currently the Director of Solid State Photonic and Quantum Technology Division within the EC department. He's also a council member of the LIGO Scientific Collaboration and directs the NU branch of the Department of Defense and of Excellence in Advanced Quantum Sensing. He received his Bachelor of Science, Master of Science, and PhD from the Massachusetts Institute of Technology, and he has a number of journal papers. He has about 56,000 citations, and he's a fellow of SPIE and OSA. Particularly, he, as you know, that for laser interference gravitational observatory, there was a Nobel Prize in Physics awarded in 2017 after first detection of the gravitational wave. So Dr. Shahriar has first-hand experience in working in the project, and I'm sure he'll going to be talking about more on his talk today. So the way today's webinar would work, that we have a pre-recorded talk that Professor Shahriar has sent us, and he's also joining us online. So after the talk, we would have, during the talk, I'll encourage you not to interrupt and ask questions if you have any in the chat box. After the video recording is played, we would invite Dr. Selim Shahriar to answer the questions. So please write your questions in the chat box. So without further ado, let's listen to the talk.
Good evening. My name is Selim Shahriar. I'm a professor in the Electrical and Computer Engineering Department at Northwestern University in Evanston, Illinois. I also have an appointment in the Physics and Astronomy Department. And thank you very much for joining me for listening to this talk. And thanks to Professor Chaudhary for inviting me. Now, as many of you know, I'm originally from Bangladesh. I left Bangladesh when I was 18 years old, right after finishing college, or what we call high school in the US. And so I am very used to giving speeches in English. So if you don't mind, I'm going to deliver my talk in English. But if you have to ask questions, you can ask me in Bengali or English. I wouldn't mind. Okay. And again, this is a pre-recorded talk, but I'm going to be present live during the playback of this talk. So you can always interrupt me and ask me a question. Okay. All right. So let me get started. Bear with me for a little bit of the technicalities here. I need to get set up. So, hide meeting control, slideshow. Okay, so what I'm going to talk about are something called superluminal and subluminal lasers for fundamental physics and applications from gravitational wave astronomy to search for dark matter and some ideas in between. And so let me just get started right away. So the big picture is we are trying to understand physics beyond the standard model and general relativity. And there are several ways to go about it. So one way to think about it is let's say that you have a clock and you're trying to understand how it works, right? So you can take two approaches. One is where you just take a hammer and smash it, as I'm showing on the left, or you can look at it very carefully and figure out what is going on. Okay. So the smashing approach is what is done in experimental particle physics, where you make these very large colliders, such as the Large Hadron Collider in Switzerland, Geneva, and France. I visited that a couple of years ago. It is a great place to visit. So it is a 15-mile circumference loop, and there's a little picture of what's going on in the loop. And what you do is you accelerate protons in two directions, and then you smash them on the very close to speed of light, and a lot of particles come out, and you look at those particles and figure out what is going on. Of course, this is a very useful way of doing it, but it runs into a limit because you can only make these loops so big. After it's very difficult to make it much bigger, and eventually you're going to run out of room. You wouldn't be able to make a larger accelerometer or collider. So you must have a different approach for going beyond what these accelerometers can do. Okay, and that is the precision metrology field, where you just measure things very carefully to figure out what is going on. So one example of that is I've shown here as a cartoon, is where an electron is trapped in a pinning trap, and you measure the magnetic moment of the electron and to verify predictions of standard model and see if there is any violation of that. So this has been often cited as the most precise test of fundamental physics or standard model, with the experiment agreeing with theory up to 12 decimal points. And currently, the best experiment on this is being carried out at Northwestern by Professor Gabriel C. So what we are doing in precision metrology is similar to this, just making devices that can measure things very accurately. Okay. So now, what are some of the big challenges in the fundamental physics? So here's some simple examples. One of them is called measuring the lens-Thirring rotation predicted by general relativity. It says that there is some rotation that happens near Earth, which is so small. Now, how small is it? I have written it 4 times 10 to the minus 14 radian per second. But physically, what that means is that this thing is rotating once in every 5 million years. It's incredibly small rotation. I need to measure that very accurately, okay, to test whether general relativity is correct or not. The another one is the gravitational wave strain measurement, which is very weak. So it produces a displacement of mirrors by a distance of 10 to the minus 18 meter or less. Now 10 to the minus 18 meter is a 100 millionth of the diameter of an atom. Okay, so it's extremely small. And now the LIGO has been able to measure something like that, but there is a need to go measure even much weaker gravitational wave strain. The another field is where you are trying to measure whether fundamental constants are varying with time, as predicted by some theories, including string theory. And for that, you need to make clocks that are so stable so that it has a stability of 1 part in 10 to the minus 18, and or even better. And people are making clocks to reach that kind of stability. And then another challenge is looking for dark matter. It turns out that the universe is filled with matter that we cannot see. And there's indirect evidence for that. And people are trying to develop experimental tools to detect these objects, which cannot be seen using ordinary techniques because it does not absorb or reflect electromagnetic fields of any kind. So these are just some sample examples of extremely sensitive experiments that are tools that are needed to do this kind of measurement. So the particular approach we are developing is based on something called fast light, as well as its cousin called slow light. Now, so what is a fast light? Fast light is where the group velocity of light far exceeds the vacuum speed of light. Okay, but it does not violate causality or relativity. And I'm making a joke here that it's not made out of tachyons, because in science fiction you have seen these things called tachyons that move faster than the speed of light. But this is nothing esoteric, exotic like that. This is just ordinary physics. Is not violation of anything that we know. Okay. So just to remind you a little bit about the various kind of velocities that are involved. So one is called phase velocity, which is the normal velocity of a plane wave. So if you have a wave of light, you can look at how the phase front is moving, and that gives the phase velocity. And in free space, it is the vacuum speed of light. But there's another kind of velocity called the group velocity, where you take a bunch of plane waves like this and put them together, and they form a pulse because they interfere destructively on the sides. And this such a pulse moves at a different velocity, and that's given by what's called the group velocity. And that's given by the speed of light divided by this quantity, which is called the group index. I have written it out separately here, which is essentially given by the derivative of the product of the index and the frequency with respect to the frequency. Now, if it is in free space, index is 1, so this becomes the same as the phase velocity or the vacuum speed of light. But if it is a material medium that has some kind of an exotic form of index, then this group index can have all different kinds of values. The group index can go close to 0 or can be very large. And when it's very large, that produces very small group velocity, which is called slow light. And when the group index is very small, it produces very large group velocity, which is what we call fast light. Now, just for completeness, there's another kind of velocity called the front velocity or information velocity. And what special relativity says is that these velocities cannot exceed the vacuum speed of light. Okay? But group velocity and phase velocity, both of those can exceed the vacuum speed of light. Okay? So now just let me show you a little cartoon of what we mean by the slow and fast light. So here is a little cartoon illustration of slow light. So light is coming through empty space, then it enters a material medium and sits slowing down, right? And here, of course, for cartoon, we're just slowing down by a factor of 5 or so. But you can make medium where it can slow down by a factor of 1 million or 100 million. And so here is another one, which is a fast light. So here again, the light is coming with the normal velocity. And once it enters, just wait a second, once it enters the medium, which is between the two horizontal bars here, it will speed up. And again, this is only speeding up by a factor of 5 or so. but the kind of material we deal with, it can speed up by a factor of 100,000 or a million. Okay, so that's what we mean by fast light. And so the obviously slow light happens in many medium, but the most dramatic slowing of light was first demonstrated using a Bose condensate by a collaboration between Harvard and Stanford in 1999. And there they slowed light down to about 32.5 meters per second. But this was not a very practical system because you cannot really use Bose condensate for most situations. So immediately following that, our group, when I was still at MIT, just before I moved to Northwestern, we demonstrated a similar effect in a solid medium, and that really revolutionized the field because now suddenly people realize that this is not just some exotic system, you can actually make it practical systems out of it. And there was an explosion of research in this field since then, and a lot of applications followed. And we achieved a velocity of 33 meters per second, so slowed light down to 33 meters per second. And then around the same time, there was a very interesting experiment done at Princeton, where they demonstrated fast light, or the group velocity actually exceeded vacuum speed of light. And I'll tell you the details of that later. But basically, what you do in that case is you produce some kind of a gain medium that has a dip in there and produces a negative slope in index that produces this negative superluminal velocity of light. Now, what we did a few years after that is to develop a very simple technique where you can produce slow light and fast light in the same medium. And here's an example of that. This is an experimental result, even though it looks like theoretical plots. So what you do is you take a, excuse me for a second, you take an atomic medium, let's say rubidium atoms, and use some optical pump to pump atoms from one state to another. These are both stable states, low-lying hyperfine states. And then you apply a pump field on one leg and a probe field on the other. And if the frequency difference matches the frequency difference between these two states, that's called two-photon resonance condition, this probe would get amplified because energy is flowing from here to there, and the pump would get attenuated. Let me activate the laser pointer again. And so here we show that as you scan the probe frequency, the probe gets amplified and the pump gets depleted as you go to the two-photon resonance condition. So a lot of things that I'm going to show you in the subsequent slides make use of this kind of a technique. So here's an illustration of what this is good for. It's called the white light cavity. A white light cavity is where you have a resonator and you fill it with some material that has this negative dispersion, where the index decreases with frequency over some range. So what happens in that case is that the resonance condition of this cavity is such that the length is equal to some integer times the wavelength of light, which can be expressed as some constant divided by the product of the index and the frequency for a material medium. So if you create a condition where the product of the index and frequency together does not change when you change the frequency because the index is going in the opposite direction, then you can create a condition where the derivative of the n omega with respect to omega is 0. What that means is that if you change the frequency, the wavelength is not going to change. It's like a magic condition. Wavelength becomes independent of frequency. So that obviously corresponds to this slope value, that the slope has to have this particular value, where n naught is the mean index and omega naught is the center frequency. But if you notice from what I said before, that this is actually the group index. So therefore, under this condition, the group index is going to 0. So the group velocity is approaching infinity. Of course, that happens only at one point, but over some range, the group velocity is large. So as a result, what would happen here now is that if I make a resonator, which is just 2 mirrors, and if there is no negative dispersion material in the middle, you would see this very sharp resonance, this blue resonance, as you tune the laser frequency. But once you activate this negative dispersion element in there, the resonance becomes broad without reducing the amplitude of the peak. Okay? So this is called the white light cavity effect. Now we demonstrated this in 2007 using rubidium atom, inside which we, let me move my picture from here, where we produce these two gain peaks in the system by using two Raman pump frequencies and one probe, so that gives you two gain. And by Kramer-Skornik relation, that produces a negative slope in the index. And so we use that to demonstrate this white light cavity effect. Here is the experimental data that we observed. Now, there is an application for this white light cavity itself in terms of enhancing the sensitivity bandwidth product of a gravitational wave detector, for example, as I will show you shortly. But there's also another very important aspect of this, which is that you can use such a system to measure the change in the length of the cavity very precisely. And that then allows us to make all kinds of sensors with it. Okay? So how does that work? So imagine first you have this ring cavity where there is no negative dispersion material here. And you have put a piece of glass in there, which can be rotated to change the length of the cavity. So then we can easily use this formula to figure out how much the frequency is going to change if you change the length a little bit, which is what's called the scale factor. So you can use this DeWalt system to measure small displacement. However, now here I have on the left, I have reproduced that system. But now if you put the negative dispersion material in there, what happens is that the wavelength now depends on the inverse of the product of the index versus times the frequency. So on the left side, which is the empty cavity case, the length change in the cavity length is proportional to the change in the wavelength, because L is equal to some integer times the wavelength on resonance. So basically the sensitivity, how much change in the wavelength corresponds to how much change in the frequency, is just given by this curve. It's almost hyperbolic curve here. So you just look at the slope of that, and you can figure out what the sensitivity is. Now here, what we have done is that by producing this index, which decreases with frequency, the wavelength now varies very slowly with respect to frequency. So therefore, for a very small change in wavelength, you get a very large change in frequency. So that means if the cavity length changes just a little bit, the frequency is going to change a lot. And that allows you to measure very small change in the cavity length, which in turn can be translated to other sensor applications such as rotation sensing, accelerometry, and things like that. Okay, so this is the basic idea. And we demonstrated that also in 2008. We showed indeed that the sensitivity varies inversely as the group index, as claimed above, right? So now, how do you translate that to measuring rotation? So there is an effect called the Sunnyac effect, which says that if you have a closed loop, here is a loop of 4 mirrors, and you have light propagating through this loop, then there's a time delay between the two paths when the system is rotating. And this is due to relativistic time dilation effect. You don't need to get into the details of that. It's a well-tested theory. So when you use that theory to observe a resonance in such a cavity, what would happen is that you send one laser, which is going in the counterclockwise loop and coming out, and you tune that to resonance, and you take another laser, send the other direction, and also make that resonate, and then look at the bit frequency between these two lasers. So if there is no rotation, this bit frequency should be 0. But if there is rotation, because of this Sunnyac effect, the bit frequency should be non-zero. One frequency shifts to the left, one to the right, and that is given by this well-known expression that has to do with the proportional to the rotation rate and the area. And so therefore, you can measure rotation using this approach. Okay? So what we have shown in 2007 in this paper that I have shown below is that if you fill this medium system with some medium that has negative dispersion, then this frequency shift gets much larger for the same amount of rotation. So that allows you to measure much smaller rotation than you could otherwise. Okay, so essentially it gets enhanced by the factor of 1 over the group index, which we call zeta, and we have shown that this factor can be as large as 1 million or even larger. So now, for some technical reasons that I'm not going to go into, it turns out that the best way to make such a rotation sensor is to make a superluminal laser rather than use just the passive cavity. Okay. So what is a superluminal laser? It's essentially the same concept as the white light cavity I mentioned before, except that it's active, meaning that you take a cavity, first you put a gain medium in there, which will make a laser, and then you put a negative dispersion element in addition to the gain medium. So now the laser itself would experience the negative dispersion, and such a system is much better as a gyroscope than the passive case I showed before. So there is a comparison of the system with and without negative dispersion. So if you don't have negative dispersion, the bit frequency that you would see in the lasing in 2 directions would be some factor, scale factor, times the rotation rate. Okay? But if you apply this negative dispersion medium or activate it, then that scale factor would be larger by this factor zeta, which is, as I said, can be as large as 1 million. So this can now measure rotation almost 1 million times smaller than what you can do with the regular gyroscope. Now there is a little bit of a catch there, because how small a frequency shift you can measure has to do with the fundamental uncertainty of the laser frequency, right? You cannot measure anything smaller than the fundamental noise in the laser. That's called the Charlottesville's line width, which I have written down here. So here, it is important that when you are making this superluminal laser, this line width does not get broadened compared to regular laser. And we have shown that that is indeed the case. So you get this enhancement, but the line width does not get broadened, so you can measure much smaller rotation. Now, how do you make such a superluminal laser? So the basic idea is that you need a gain medium that has a dip in the center. And if that happens, then you can show by, again, the Kramer-Skolnick relation that there would be negative slope in the index, which I have blown up here. So how do you make a laser that has a gain medium like that? It's not easy, because this has to be very narrow, like a few megahertz wide. So typical solid-state gain medium or diode laser gain medium cannot be tailored to do that. So, but if you can make it behave like that, then we have shown that it does indeed behave like a superluminal laser. And here I have shown a simulation that shows that the sensitivity is enhanced by a factor of almost 100,000, and you can even make it even larger. So again, how does this become more sensitive? It's the same idea that I explained before. If you have the laser here, again, the wavelength depends on the inverse of the index versus the frequency. So for a conventional laser that doesn't have negative dispersion, the sensitivity is given by the inverse of the slope of wavelength versus frequency. And when the laser becomes superluminal, this wavelength becomes almost flat with respect to frequency. So the slope becomes very small, so it becomes a lot more sensitive. Now, how do you make such a laser like that? There are several different ways. The first approach that we used is described there. It's a little bit complicated, so let me take you step by step. So this is a ring cavity, 3-meter cavity, and there's an optical diode, so it can laser only in one direction. So you get one cell where you use some kind of a mechanism in a atomic vapor to produce a broad gain. And then you take the output of the laser, shift its frequency, bring it back into the cavity, which produces another beam, and then you use another cell, which again has another kind of atomic medium that reduces the gain for this lasing beam in the presence of this green probe beam, which again is due to the Drummond effect that I showed you before. Okay. So the combined effect is that the gain profile for such a system does indeed look like what we want. And by contouring the parameters, you can tune the width of this resonance and the depth of this resonance to get any dispersion you want. So here's just a little more detail. So the cell that produces the broad gain was using something called the direct pump alkali laser technique, where you optically pump atoms from the ground state to some excited state and add a lot of buffer gas at a very high pressure, like 1 atmosphere or 2 atmosphere. And then the atoms relax quickly to produce a population inversion at 795 nanometer. And that gives you this broad gain, but without the dip. And then in the second cell, you use that Raman process that I presented before, is the 2-frequency resonance, that in the presence of the probe, the pump is depleted, which produces this dip in this gain profile. And so together, they give you the desired profile. And so this was our first experimental setup. So here's a picture of the experiment. Here's a schematic diagram. Again, I'm not going to go into the details. It's basically what I just described. And in the experiment, we indeed saw a dip in the gain. And of course, this is not as nice as what I showed you in theory because of some asymmetries in the system. But nonetheless, it did produce the conditions that we wanted. And the theory and experiment matched to some extent, not perfectly. We achieved an enhancement of about a factor of 200 using this technique. So this was the first demonstration of a superluminal laser in our group in 2016. And then we realized that this technique had some limitation because if you remove that optical diode, it would try to laze in both directions at the same time and produce gain competition. So to eliminate that problem, we came up with a new technique where we use 2 isotopes of rubidium, and again, this Raman process that I explained before, to produce gain using one isotope and to produce depletion using another isotope. And so both isotopes are present in the same vapor cell. So you get this from one single cell, and this process is directional gain. It only works in the direction of the pump, so it does not produce a counterpropagating laser. So, and then we have carried out simulation, and it indeed shows that you have this produced nice gain with a dip, and there's a sharp dispersion, and you can get an enhancement by a factor of as much as 3.5 times 10 to the 6. So to make a gyroscope out of that, this is the experimental apparatus you need. You need a ring cavity, you need 2 rubidium cells, and inside each cell, this kind of gain and depletion going on this side, and gain and depletion going on this side, but no crosstalk between the 2 directions. And using that approach, you can now make a gyroscope, or also if you mount one of the mirrors on a spring, then it will move when an acceleration is applied, so you can also measure acceleration simultaneously. So that's why we call this a superluminal ring laser gyroscope and accelerometer. And here is one of the experimental implementation of that in our lab. Of course, looks very busy. It requires all these lasers to do all this optical pumping in different directions and Raman pumping. And so we have a custom-made gain chamber where we have rubidium cells in there, and this worked quite well. So again, as we tune the condition, we saw indeed there's a dip in the gain profile, and then we improved the system. Here's a better result. So this is in one direction, and this is in the other direction, both working simultaneously. Again, there's another version of the same result. And here is the result where we got quite good matching with theory, and we got roughly a factor of 650 enhancement in each direction. So this would become now a gyroscope that is a factor of 650 more than what a conventional gyroscope would do. And there are some issues there. In order for this thing to work well, all these lasers that we're applying, the red laser, blue laser, these all have to be phase locked, even if they're different frequencies. So we have to use something called the offset phase locking technique, which makes it even more complicated. Anyway, those details don't matter. So once we implemented that, we got even better result. So now we can see a sensitivity of up to a factor of 3,000 almost in this system. And so the nice experiment with theory, and the big sensitivity enhancement is of course almost 1,000. So now, of course, this apparatus that I showed you is on a table, occupying a big optical table. So that's not a practical device, right? So what we have been also working on is making chip scale components like lasers, detectors, modulators, all built on a chip. Unfortunately, that technology does not exist at this wavelength. So we have to make these lasers ourselves. So we have a new grant from the Air Force Office of Scientific Research to make these chips ourselves. So the vision is that once you have the chip made, and so there will be these two gain cells, one here, one there, and there is the additional cells for stabilizing the lasers. And so this would be one gyroscope. It would be very small size because of this chip scale lasers. And then you can take three of these to measure rotation and acceleration in three directions simultaneously. Now, why do you need that? So one of the big needs especially in the defense field is for navigation without GPS. Now you know about how GPS navigation works. You have all these satellites that are floating around. Let me turn the laser pointer off. There are like 24 satellites flying around at any time, and your car here communicates with the satellites and takes signals from at least 4 of them, not 3. Actually, we have only shown 3 here, but takes signal from 4 of them to essentially triangulate your position. That's how GPS works. Now, what if the GPS stops working? Because if there's a war breaks out, it is very easy to jam GPS, or somebody may even shoot down your satellite. Then how would you navigate under those conditions? So the way you would do that is the following. Let's say you are driving a car. Now, if you know your acceleration, you integrate that to find velocity, integrate that to find position. So by keeping track of acceleration carefully, you know exactly how far you have gone. But if you rotate it, then you might get away from where you're trying to go. So you also need to measure your rotation carefully. So if you can measure both acceleration and rotation carefully just from inside your car, then you don't need any GPS. You can figure out where you are starting if you knew where you started from. So that is called inertial navigation under GPS denied condition. So for that, you need this very accurate gyroscope, rotation sensors, and accelerometers. Okay, so a lot of planes already use those kind of systems as 3 accelerometers and 3 gyroscopes. They use that to navigate. But these things are not perfect yet. There's a lot of improvement that's still to be done. Even the best one that you can buy are not quite good enough for some applications, and they're very expensive and very big. So this is one of the state-of-the-art gyroscopes that cost $1.5 million, and it's about this big. Okay? What you need is a much smaller unit, but even more sensitive than this system. And that's what we are building. So it's an artificial rendition of what we are building right now. These are the 3 systems, and these are the electronics that control the operation of the system. And if you could do that, you could meet many of the defense needs, or also commercial needs, and needs for NASA for navigating spaceships, missiles, planes, even shells from tanks and stuff. They all can be guided by very small and precise gyroscope of the accelerometer, gyroscope and accelerometer that we're making, which we call the superluminal inertial measurement. All right, so that is some of the practical applications of this technology, where a lot of our funding comes from in the Department of Defense, NASA, DARPA, and all that. But there are also applications to fundamental physics, as I advertised at the beginning. So using these devices, you can test general relativity as well as carry out gravitational wave detection astronomy, gravitational wave detection and gravitational wave astronomy. So let me tell you a little more about that. So what about general relativity? Okay, well, it's a theory, and Einstein's theory, most of you obviously know about it, and some of you are experts at it. But it is not, people are not fully comfortable with it for 2 reasons. One is that it hasn't been tested under all different conditions, especially on a very large scale situations like in galactic dynamics. And there are some questions whether this is really accurate on that scale. The second, it is not compatible with quantum mechanics yet. So at some point it breaks down. And so there is always this question of testing general relativity very precisely to see when it starts disagreeing, experiments start disagreeing with theory. So that is one of the motivations. So one of the things that we are testing is this measurement of lens stirring rotation. It's called the gravitational frame dragging effect. So what it says is that if you have a rotating object, so let's say this is Earth, and you have a gyroscope next to it, which is rotating, but it will nutate at a small rate due to the rotation of the Earth. Okay. Now that is called the gravitational frame dragging effect or the lens stirring rotation. And it's a very simple formula to figure that out. Has to do with the Schwarzschild radius and the radius of the object of Earth in this case. And you can calculate this number, and it comes out to be, as I said, very small, one rotation in 5 million years. Okay, and so you need a gyroscope that is sensitive enough to measure that. Okay, so people are trying to do that. Sorry about this chiming sound that I forgot to turn off. So people are trying to make optical gyroscopes that are very large in area. Remember, the larger the area is, the more frequency shift you get for a given rotation. And even if you make it like 20 meter by 20 meter size, you still be like 2 orders of magnitude smaller than what you need to measure this effect. Okay. And when you try to make a gyroscope that big, there's all kinds of instability that comes into play. So what we are working on is using our technique, which is has this inherent built-in million-fold enhancement in sensitivity. So even if we make it like a 1 meter square version of the gyroscope, but it's very stable, then you should be able to measure rotation even a lot more accurately than what is needed for measuring the lens stirring rotation. So this would allow us not only to confirm the general relativity prediction, but also to see if at some point it starts breaking down. Let's say after the third decimal point or fourth decimal point, you start disagreeing with the theory. So that is the goal here. Okay. Now, just a little side story. There's another kind of gyroscope we're developing that does not make use of slow and fast light, but uses atomic interferometer. And what happens there is you start with a bunch of atoms, like 100 million atoms, and use a process called spin squeezing to create a what's called a Schrodinger cat state. So it's the same macroscopic object has two different identities, quantum mechanical identities. In one, all the atoms are spin down, and the other one, all the atoms are spin up. And so this system acts as an object that has an inherent frequency similar to the optical frequency. So the center of mass of this object oscillates at a frequency of 10 to the 33 hertz, which is 19 orders of magnitude larger than the optical frequency. Okay, and the theory is otherwise the same. So therefore, this system would be that much more sensitive than the optical system. Of course, there will be some other issues coming because in the optical case, you have a lot of particles and you have essentially one particle. But even when you take all of those things into account, this would be a lot more sensitive than the optical gyroscope and would be able to easily measure the lens stirring rotation. So this is one of the other experiments we are working on in our lab. So now getting back to the slow and fast light issue. So as I said, one of the application is in the context of gravitational waves. So of course, gravitational wave has been detected, but that is not the end of the story. That's actually the beginning of the story. So the real goal is to use gravitational wave detection to enhance our understanding about the universe. You know, what's going on during black hole collisions and what's the origin of mass formation and all that. But there is a really overarching objective, which is to understand what happened immediately after the Big Bang. So, you know, when you use a telescope to look far in the distance, what you're really doing is looking back in time, right? So if you look at something that is 10 billion light years away, you're actually looking at things that happened 10 billion years ago, right? So by that extension, you should say, okay, I should be able to see things that happened right at the Big Bang, right? If I look far enough. But that's not the case because up to 3 minutes after the Big Bang, no light could escape because of the density of the system, so that all light got absorbed. It's only after 3 minutes you can see. So as we make better and better telescope, we should be able to see closer and closer to what happened after the Big Bang, but no closer than the first 3 minutes, okay? And a lot of the interesting things, such as the inflationary expansion of the universe, happened during that time. Now, gravitational wave was not bounded by the same effect. So gravitational wave actually could spread out. So if we could detect gravitational wave, then we can see all the way back to the Big Bang theory, right up to the instance of the Big Bang, and that is the goal. Okay, so again, the what we're working on is to be able to detect extremely faint gravitational wave and create a map of the stochastic gravitational wave around the world, and from that try to understand exactly what happened at the Big Bang point. Okay, and so that is the primary goal, driving force. So therefore, there is a need to make better and better and more and more accurate gravitational wave detectors, even though gravitational wave has been detected now. Okay, so just a little reminder about a gravitational wave. The way to illustrate is, so here is an object that has a producing gravitational field. So this other object is seeing that. But if this object moves around, the overall gravitational field is going to be due to the both of them. And since they are moving around, the gravitational field is going to change, right? So if they rotate at a certain frequency, so the gravitational field is seeing the ripple. So that is what is the gravitational wave. And it can just spread out and go through the universe without getting absorbed, right? So now, and there's a video that I wanted to show you. This is an actual simulation of the merger of two black holes. That was the first instance of the direct detection of gravitational wave. So you'll enjoy watching this video. So watch. So these are two black holes that are spiraling around one another. And as they get closer and closer, they move really fast. Even these are massive objects. Each of them is like 10 to 20 times the mass of the sun, but it is spinning at a rate which is almost one-sixth the speed of light. Okay, so this massive object is moving that fast, and then eventually they come close together and form a single black hole. And during this very last stage of this, it produces strong enough gravitational wave that we can see it from Earth. Okay, and that is what we was seen in 2016. Here is the data from that 2016 paper. I was fortunate enough to be a co-author of this paper. And this signal that you see is the gravitational wave produced during that very last part of that merger of the two black holes. And of course, 3 people received the Nobel Prize for that, people who started this project very, very early on. And the primary person is Ray Weiss. And there's a picture of me with Ray at a dinner when he came to visit us recently. And I have a personal connection to him because aside from my professional connection, on the right, you see a picture of me and my thesis advisor, who actually unfortunately has passed away. His name is Shaul Ezekiel. So Ray Weiss was Shaul Ezekiel's advisor. So Ray is actually my grand advisor. He was also on my thesis committee. So I have been with these gravitational wave people ever since I came here. Anyway, so now how do we make it better? So the way the gravitational wave works is if you have a ring and the gravitational wave comes and passes through the ring, what would happen is that the ring would get squashed in one direction and then get squashed in another direction, oscillate like that. Okay? That's called quadrupole radiation. And so to measure that, you make these 2 orthogonal interferometers. And so one arm of the interferometer gets longer, other one gets shorter if the gravitational wave is coming perpendicular to you. And that's the natural way to detect it. And let me show you a quick video of what this interferometer is. So essentially a Michelson interferometer. The light comes in, gets split up in 2 ways, and a part of it leaks out, and gravitational just makes them move back and forth like that. And now just a little more detail. So there's a sinusoidal wave going in one direction, another one going to the left, and they reflect by the mirror and come around. And then on this beam splitter, they mostly cancel each other in the output port, but a small amount leaks through if there is a mismatch in the length of the 2 directions. Okay, that's called the dark port. And as the 2 mirrors move even very slightly, there's a small amount of light that comes out, and the modulation of that amplitude of light is what we detect, which is the signal you saw in that slide couple of slides ago. Okay, so that is basically the story of a gravitational wave detector. It looks very simple, but it was extremely difficult because there are all kinds of noises in the system, and you have to design this apparatus so carefully that all other small perturbations would be negligible compared to this very small displacement that you're trying to measure. Okay, so the actual apparatus looks sort of like this. There is a one arm of the Michelson Interferometer on the vertical direction. May activate my laser pointer again. And another arm in the horizontal direction, and there's some additional complication to account for all these noises that exist and improve that. But it is fundamentally a resonator in addition to Michelson interferometer, because inside each arm you have a resonator. What that does is it makes the light bounce back and forth inside each arm many times before it comes back. So effectively increases the length of each arm, okay, which makes it more sensitive. Okay. So as a result, what happens is that it has a very narrow response band, okay, because it's a cavity resonance. So you can only see gravitational wave over some small range of frequencies. So what we can do is, using that white light cavity concept, make the sensitivity broader without reducing it. So it enhances the sensitivity bandwidth product. Okay? And that's why I showed you that white light cavity. So this would be your basic resonator, and the white light cavity makes it broader, increases the sensitivity. And I will not go through the technicalities, quite cumbersome and details, but basically you take your basic LIGO apparatus and add an extra mirror and put some negative dispersion element in there, and that produces this effect that we want to see. And we showed early on that if you do that, your sensitivity goes up a little bit and it becomes much broader than what a normal LIGO apparatus would do. And then we delve into the more details, and so here's an actual configuration of how our system would work. And then we showed that, see, this dotted red curve is the LIGO sensitivity. It's a very narrow band here, and our approach broadens that significantly, and so we get a net factor of almost 18 enhancement in the sensitivity bandwidth product. Now, why is that important? Because let me show you the next slide. So imagine that the red dot is the volume of the universe that you can look at with this narrowband detector. Okay? And let's say in the broadband detector, you have increased the sensitivity by a factor of, say, 17 or 18. So what that means is that you can look, because gravitational wave intensity signal also at 1/r, not 1/r square. So you can look a factor of 17 farther away in each direction, right? So in volume, you get an enhancement by a factor of 17 cube, which is almost a factor of 6,000. So by enhancing this sensitivity even by a factor of 18, you are increasing the volume over which you can see gravitational wave by almost a factor of 6,000, okay? So I'm almost running out of time, so I'm going to try to wrap up it quickly. So this is one thing we're working on, but we're also developing another kind of gravitational wave detector where we make two superluminal lasers that are perpendicular to each other. And now we look at the frequency difference generated by the lasers, not the Michelson interference. And that becomes even more sensitive. And our simulation of this system shows that it's even a lot more sensitive than the LIGO, which is the black curve, and much broader in the sensitivity. And so we need to make better and better superluminal lasers to make this work. And one of the key advantages of this approach would be that it can be very small, only about 1 meter long. And so last topic, and it take a couple of minutes, is something called a subluminal laser. Now that is just exactly the opposite of a superluminal laser. So all you need for a subluminal laser is just a very narrow gain spectrum, okay? Or just a broad spectrum with a narrow peak on top of that, okay, as opposed to a deep. So a basic Raman laser that I showed you before already acts like a subluminal laser. So it's exactly the same effect, is the opposite of that. The sensitivity is proportional to 1/the group index, but here group index is larger than unity. So the laser, instead of becoming more sensitive, it becomes much less sensitive. And I'll tell you why that is useful. So we carried out this experiment to make a laser and showed that when you scan the length of the cavity and you can measure the change in the frequency and you compare that with the regular laser versus the Raman laser, You see that the regular laser would be like this slightly slanted dashed curve, and the Raman laser would be almost flat black curve here, so it's much less sensitive. So change in the frequency as a function of the change in the length is much smaller. So we achieved a sensitivity suppression factor of about 600. In fact, in one case, we went up to 663. But if we use a better cell, which we are working on now, we should be able to suppress it by a factor of at least up to 1 million or 10 to the, 10 to the 7. Now, why is that useful? So one of the interesting aspects of this laser is that the fundamental quantum noise limited line width drops off as 1 over the square of the group index. So if we have a group index of 663, the line width would be reduced by a square of that. So if you start with a line width of 1 hertz, the line width of this laser would be like 1.2 microhertz. Unfortunately, we don't have any technique for measuring such a small line width. But if you could do that, this could produce the most stable laser in the world. And that could be used to improve the performance of the best clock that currently exists, which are called optical clocks, where you stabilize a laser to an atomic transition, but it is limited to some extent by the fundamental uncertainty of the laser frequency itself. So this laser would improve that very significantly. And the last application that I'm going to talk about is the search for dark matter. Now, what is dark matter? So if you look at all the matter and energy in the universe, so about 60 or 70% of that is dark energy, which we cannot see, and 31% is matter. And of that 31%, only 20% is the regular matter. Okay? So we are only about 5 or 6% of the all matter and energy in the universe that we can see. All the light and matter that we see only constitutes 5 or 6%. The rest of it is something that we know indirectly they exist, but we have no idea what they are, what they look like, how they behave. Okay, and so there is evidence of that. The evidence is the following. So if you have a galaxy and you look at the stars, they're spinning around the center of the galaxy. As you go farther away, the velocity of that should be falling down because your centripetal force is becoming smaller and smaller. But experimentally, people found that it actually increases. And the only way you can account for that, if you follow general relativity accurately, that there's a lot more mass that we cannot see in the galaxy. And that, of course, includes us here, because we are also in the center of a galaxy, right? So we're all imbued by this dark matter, but we don't know what it is. Okay? And there's also other evidence of this. Now, there's also one possible alternative explanation that there is something wrong with general relativity. So that is where the test of general relativity also comes in. But there are so many different evidences of indirect evidence of dark matter that most likely it exists. And so people are trying to find it, okay? But because it doesn't absorb light, doesn't reflect light, it is almost impossible to figure out how to do it. So people have been working on theories, and there are various kinds of proposed dark matters, scalar boson, vector bosons, and so on. And we are working on detecting the scalar boson type using this following technique. So the idea is that this dark matter acts just like a classical wave, and when it hits you, it changes the fundamental constants of nature, like the fine structure constant. So that would mean that the size of atoms would change momentarily, okay? So if you now do an experiment like this, you have some laser coming in, you split it in 2 ways. One goes to a cavity, 2 mirrors, but the center part is a rigid medium, and the other one where the center, these 2 mirrors are suspended with some springs from the ceiling. So this one would increase and decrease in length as the gravitational, the dark matter goes by, but the other one would not, because the spring would damp that fluctuation. Now, what we propose to do is say that, okay, we forget about this second cavity. What we do is we start with a subluminal laser and send that light to this cavity. Now, the subluminal laser, when the physical length of it changes, the frequency of it is not going to change, because it's going to change by much smaller factor because of the suppression of the you know, length to frequency conversion. But this one would change very significantly. So just by looking at change in the cavity transmission of this cavity, you would be able to detect dark matter. And that is what we are working on with a couple of colleagues at Northwestern using this subluminal laser. So that's basically the end of the story. Here is a somewhat dated picture of my group. I have an updated picture. A lot of them contributed to the work that I presented, so I figured I'll show you an older picture of these people. And there's the summary. The bottom line is a superluminal laser is a very highly sensitive to cavity length change, and it can be used to make very sensitive gyroscope and accelerometers for inertial navigation as well as for measuring lens-throwing rotation. Can also be used to make tabletop super sensitive gravitational wave detectors, and we have achieved a sensitivity of up to a factor of 3,000 so far. And the related technology is the subluminal laser, which what we have seen is subtraction factor of almost 700, and it can have very small line width, which can be used to make better atomic optoatomic clocks or look for dark matter. Okay. Well, thank you very much for listening. And if you have any question, as I said, I'm live while this video is being played, so feel free to ask me. Okay.
Thank you very much for listening to the talk. And we actually have Professor Shahriar among us, so I would like to invite him to take.
First, let me say hello to everybody. As I said, I feel if you have to ask me any question, you can ask me in Bangla. I'll probably respond in English because you'll find out if you live in another country for a long time, and all you do is talk all the time. You know, that's what professors do, right? It is very difficult to speak in another language, even if it is your mother tongue. So, and thank you all for listening to the talk. I know the pandemic situation in Bangladesh is not very good right now. So, but thanks again for listening. So if you have any question or comment, I'd be happy to respond. Otherwise, I know that a lot of you are students at BUET. So once you graduate, feel free to apply. Last time when I went to BUET, I gave a talk in 2010, and there was one student who came by to see me, and then later on she ended up in my group. So if any of you are really interested in this kind of work, you know, feel free to apply to Northwestern, either to work in my group, or there are many other professors in various optics. Yes. Was there a question from someone?
There is a question from Saiduzaman Abir. So Abir, you can go ahead and ask it to the professor.
Okay, go ahead. Is this a question in the chat?
Yes, I can read it out actually.
Okay, so, sure. I can barely hear you, by the way, so go ahead.
Yeah, so I'm really enjoying the talk. Thank you to Professor Shahriar for a nice demonstration. So regarding the first part, I must have missed the frequency range of the gyroscope or WLC's work. Could they be mentioned again?
The frequency range of the gyroscope for, hold on a second, I'm not sure if I follow the question. Frequency, can you repeat that last part again?
Yes, sure.
Okay, I can read it. Okay. Yeah. It says I must have missed the frequency range the gyroscope WLC's work. Okay. So I'm not sure what you mean by the frequency range. So typically, the center frequency depends on what medium you're using. So for example, our cavities are made using rubidium atoms, and the resonance frequency, we think more in terms of wavelength. Of course, you can convert that to frequency, is a 795 nanometer. So all of these processes are centered around that frequency. Now, how broad you can make it depends on the width of the dip. So in our case, these dips are very narrow. It's about 2 to 3 megahertz wide. So we start with a cavity that would, let's say, have a line width of 100 hertz, and we can broaden that to 5 megahertz. Now for gravitational wave detection, that's all you need. You need to start with a cavity that has a width of about few hundred hertz, and you want to broaden that to about 4 kilohertz. So that kind of broadening is good enough for gravitational wave. Now there is another application that I did not mention. It's for optical data buffering, high-speed optical data buffering. For that, you have to make a white light cavity that's much broader and works around the telecommunication wavelength, the 1550 nanometer. And in that case, we can make it with a width up to 30 gigahertz. But that requires optical fibers using Brillouin scattering, or you can do it with the rubidium vapor, but then it would be around 795 nanometer, and you would need this very high pressure buffer gas with like 10 atmosphere of pressure. So these are kind of very difficult to realize technologies, and my focus nowadays is more on this fundamental physics test. I'm not sure if it was the proper answer to the question, but
Abir actually said again that he cannot speak as he has audio issue in the Zoom.
Okay, so go ahead and write.
Yeah, he said integration of the tabletop setup was difficult as the integrated circuits are not made in the WLC frequency range. Would transducing help in the optical integration?
So Sajid, I have a very hard time hearing your talk as you speak. So you are asking about.
Let me switch to my phone.
Oh yeah, that's much better.
Okay.
Okay.
So I'm sorry, I cannot speak if I have issue in Zoom. I can write. As Professor Shahriar was saying, integration of the tabletops was difficult as the integrated circuits are not made in the WLC frequency range. Would transducing help in the optical integration?
Well, so first of all, the optical integration work that we are doing, the kind of component that I mentioned, those kind of components have been developed for the telecommunication wavelength range in the 1550 nanometer. But we need all these lasers at 795 nanometer. Now, when I think you meant transduction, meaning converting from one frequency to another. Is that what you meant? I assume that's what you meant. Yeah, so he's saying yes. In some situations, transduction would be useful. In this case, I'm not sure if it would be because the transduction technology itself would be so difficult that it would be much easier to make the actual laser. So for example, if I say, okay, I have all these chip scale lasers at 1550, and I'm going to shift the frequency to 795, that is not easy, right? Because there is no simple modulator that would change the frequency. Sometimes you could do something like frequency doubling. So if you happen to have the wavelength that after you do frequency double would come to 795, that can be used. But generally speaking, when you do frequency doubling, you get very little power in a very inefficient process. So in principle, that can be done, but this process, this optical pumping of the atoms takes some power, like 100 milliwatt kind of power, and some of them, and the rest of them about 20, 30 milliwatts. And the nonlinear processes hardly produce that kind of power. But that is not an impossible solution. But all things being equal, of which they're not, I think developing these components directly at those wavelengths on a chip is the way to go. But that's not easy either. We have started working on this for a couple of years, and making the diode lasers and the waveguides and modulators at these wavelengths is not easy, because it is hard to find a nice transparency window in the solid state medium for those wavelengths. I'm not sure if that answered your question, but that is what I can say from what I understood your question to be. Okay.
All right. Yeah, he said thank you, and for he thanks the speaker for the detailed insight. Is there any other questions from the audience? You can go ahead and ask to the speaker directly. We don't have a large audience today, so please go ahead and ask. I guess we don't have any other questions. Dr. Ahmed Zubair Bhai is here. Can you hear me? Okay. I'm sorry, Dr. Zubair. Actually, probably he's away from the computer. He asked me to share the screen with the audience a little bit to have a brief announcement for our upcoming event, which is happening on August 6th. We are also continuing this Enlighten Bangladesh webinar series, which is on compound semiconductor based classical and non-classical light emitters and visible through infrared. And for today's talk, it was a really insightful discussion regarding the application of superluminal lasers for detecting gravitational waves and black hole. I sincerely thank Professor Shahriar for the talk, and even though the audience is shy today, I see a lot of our undergraduate and master students who could join today. So I encourage you, even if you have a question you couldn't ask today, to write to Professor Shahriar and email him regarding your question and discuss further if you're interested to work in this field.
Yeah, so I would also like to repeat that I am not hard to reach. Some people do not publish the email address and stuff. I am not like that. So my email address is just my last name at northwestern.edu. So if any of you would like to know more about what I talked about or would like to communicate with me, feel free to do so. I'm still very much a Bengali at heart, even though I'm not speaking in so sorry about that. But feel free to get in touch with me anytime, okay? So if that is it, then we can say goodbye, and then hopefully we'll see
Yes.
when I come to Bangladesh.
Yeah, definitely. We would love to host you live in front of a live audience in Buet or some other universities when you come to Bangladesh. So let's keep in touch. And without further ado, I would like to really sincerely thank your presence today and for the wonderful talk. And I would like to conclude this session. Thank you, everyone.
Thank you, everybody.
Oh, there is actually another question
for address in chat. Okay, I'll type that. So I have obviously many different email addresses, but if you send it to this one, I would get it. Okay.
Thank you very much. So this is Shahriar at northwestern.edu, as the professor mentioned. So with this, I would like to conclude the session, and thank you everyone for joining us.
Thank you again, everybody, for listening. Take care then. Bye.